All right, so section 4.3 is logarithmic functions. So for all real numbers y and all positive numbers a and x where a is not equal to 1, y equals the log base a of x, which is equivalent to the exponential form of x equals a to the y. Notice that all the variables are the same and we go from using a log to having an exponent. That makes it easier to put in the calculator, by the way. So the expression log ax represents the exponent to which the base a must be raised in order to obtain x. The number a is the base of the logarithm and x is the argument of the expression. So for examples, let's practice going from log form to exponential form. So you take the base, and then you take the number that's over here, and that's your new exponent, and it's equal to this number right here. So 2 to the third equals 8. Take your base, 1/2, since it's a fraction, and this is your exponent to the negative 4 equals 16. 10 to the 5th power equals 100,000. Now, how do you go backwards? So we know we're going to have log. So we had log, and then the base was the big number, so that's going to be 3. So your base is 3. This is the part that goes here. So log base 3 of 1 over 81 equals, and then the exponent is what you're equal to. All right, let's try the next one. So log, so we had base 3, so base 5, equals 5, so 5 goes here, and your exponent is what your log is equal to. So they all just kind of rearrange places. So this is log 3/4 base 1 equals 0. So this needs a star because you're going to use that a lot going back and forth. Okay, now solve each of these logarithms. So we know that log base x is going to be x to the third equals 8 over 27. So what I know just from memory is that 2 to the third is 8 and 3 to the third is 27. So I'm going to say x to the third is equal to 2 over 3 to the third. Now, as long as they have the same exponent there, then I know that x is 2/3. B, we've got 4 to the 5/2. So 4 to the 5/2 equals x. So exactly what does that mean? Well, I know that the square root of something, we'll just say q, is equal to q to the 1/2. So what I'm going to do is turn this 4 to the 1/2, but I'm going to raise that to the 5th power. So now I've got the square root of 4 to the 5th power. I know the square root of 4 is 2, and 2 to the 5th power is going to be 32. So x equals 32. So anytime you can turn an exponent into a square root, where you get 1 to the 1/2, where you can make it a square root, sometimes it makes it a little easier. All right, this next one here, we have 49 to the x equals the cube root of 7. So what I know is 49 is really 7 squared to the x, and this is to the 1, so this is really 7 to the 1/3. So now these two have the same base. So now I know that 2x is equal to 1/3. So if I divide both sides by 2, I get that x equals 1/6. And just a quick refresher on dividing a fraction by a whole number. I'm going to do 1/3 divided by 2/1 because 2 is the same thing as 2/1. And just to go back to that elementary division, a fraction, you got 1/3 you keep, you change that to multiplication, and you flip your second fraction. You multiply straight across, and that's where the 1/6 comes from. Just a little reminder in case you forgot. All right, describe a process for solving logarithmic functions, convert to exponential form, and solve for x. So convert to exponential form and solve for x. All right, so now we've got if a is greater than 0 but not equal to 1 and x is greater than 0, then the log function with base a is f of x equals log base a of x. So y equals log base a of x. It's the same thing that we had. All right, so just some quick rules on domain and range. So the domain of log base a of x is 0 to positive infinity. So your x values are only positive numbers. Your range can be anything. If your base is greater than 1, it is increasing. And you can see that it's increasing and continuous on the entire domain. So as x gets larger, your y value will get larger. The y-axis is a vertical asymptote as x approaches 0. So as your x is approaching 0, it's going to reach that y-axis. I guess it would help if I could spell it right. R-I-G-H-T. And every single one of these graphs will pass through these points. 1 over a, -1 will be one of your points. 1, 0, and a1. So it will always go through those 3 points, whatever your base is. Now, if your a is between 0 and 1, it's decreasing and continuous. And again, you'll see that the domain is still only positive x values, but your y values are still going to be anything. The entire domain is obviously the same. The y-axis is still your vertical asymptote coming in from the right, and you still have those same exact points, whatever a is. So all of those points. So whether it's increasing or decreasing, whether a is greater than or less than, the only thing that's different is it going like this or is it coming this way? So is it above the x-axis or below the x-axis? All right, so let's talk about some characteristics. So all the points, so what we just talked about, 1 over a, -1, 1, 0, and a1 are on the graph. If a is greater than 1, it's increasing. If it's between 0 and 1, it's decreasing. The y-axis is your vertical asymptote. And the domain is positive real numbers, and the range is all real numbers. All right, let's look at graphing some of these using these characteristics. Okay, so we've got y equals log base 1/2 of x. So what I'm going to do is I'm going to do the inverse, because we practiced doing inverses on the previous lesson. So first thing here, so I'm going to write, actually I'm going to write it down here. So we've got y equals log base 1/2 of x. So this means 1/2 to the y equals x. So remember, to find the inverse, you switch the x and the y and solve for y. So if I switch the x and the y, it's going to be 1/2 to the x equals y. So this is the inverse. And remember, your inverse, it flips across the line y equals x. So if I can find the values of the x and the y of the inverse, then you just flip them and you're back to your original. So remember, you've got, this is your line y equals x. So let's create a table of x and 1/2 to the x. So if we did -2, so 1/2 to the -2. So remember the rule, 1/2 to the -2. Basically, that's like saying 1 to the -2 and 2 to the -2. And if you want the exponents to become positives, they just switch from numerator to denominator. So this is the same thing as 2 squared, which would be 4. If to the 1/2, or to the -1, so 1/2 to the -1 would just be 2. And 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. And 1/2 to the 2 is 1/4. So this would be your inverse. So now to come back and do your actual equation, you just switch all the places. So your actual graph is going to be 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So I'm going to graph the inverse in pink. So let me enlarge this a little bit. So we know we're going to go -2. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so -2. 1, 2, 3, 4. -1, 2. 0, 1. 1 and 1/2, and 2 and 1/4. So this is your inverse. And then I'm going to flip the points around. So now we got 1, 2, 3, 4, 1, 2, 2, -1, 1, 0, 1/2, 1. So that would be like right here. Oops. And 1/4, 2. Oops. So let's see. Let me back up a little bit. I think I misplotted those 2 points. All right. So we've got our 4, -2. That one is not making sense right there. Then we got 2, -1. We got 1, 0. If we come over 1/2 and go up 1, come over 1/4 and go up 2. So now this one is looking more like, oops, that's terrible. this. And notice, make this, that's the line of reflection there. So there you go. So the blue line is your function, log base 1/2 x. So I'm going to do the same thing over here. So this is, if we write it as y equals log base 3x, so this as an exponential equation is 3 to the y equals x. If I write the inverse, it's 3 to the x equals y. So this is my inverse. So I'm going to graph the inverse, get the points for the inverse, and then reverse them and create my table. So let's see. I'm going to choose -2, -1, 0, 1, 2. So this is my x, and this is 3 to the x. So 3 to the -2 would be 1/9. 3 to the -1 would be 1/3. 3 to the 0 is 1. 3 to the 1 is 3. And 3 squared is 9. Now let me get over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So just get you a few points on there. So I'm going to graph my inverse first. So -2 and 1/9. -1 and 1/3. 0, 1. 1, 3, and 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's about right here. And there's the inverse. So I know if I flip it, you're going to have your log base 3x. All right, so let's reverse all of our points. So now we've got 1/9 and -2, 1/3 and -1, 1, 0, 3, 1, and now we've got 9, 2. All right. So now we're going to go over 1/9 and go down to -2. Go over 1/3 and down to -1. 1, 0. 3, 1. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. It's about like so, and then there you go. And we know that the line y equals x is the line of reflection, so they should just be mirror images of each other over that line. All right. Graph each function, give the domain and range. All right. So here we've got y equals log 2 x minus 1. So I'm thinking, all right, we've got log equal, or y equals log base 2 x minus 1. So if I write it as an exponent, it's going to be 2 to the y equals x minus 1. And if I switch the x and the y, it's 2 to the x equals y minus 1. Solve for y. 2 to the x plus 1 equals y. So this is my inverse. So if I can create a table for the inverse, first I also want to make sure that if you take your x minus 1 and set it equal to 0, that is going to, oops, not 0, it should be a 1. Equals 0, so x equals 1. This is your vertical asymptote. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to find this, what, x equals 1. So there is our vertical asymptote. All right, so let's go in here and let's choose some x and y values. I'm going to choose a 0, a 1, a 2, and a 3. So these are my x values. And this is 2 to the x plus 1. So 2 to the 0 is 1, and 1 plus 1 is 2. Two to the 1 is 2. 2 plus 1 is 3. 2 to the 2 is 4. 4 plus 1 is 5. 2 to the 3 is 8. 8 plus 1 is 9. So there is the inverse. So 0, 2, 1, 3, 2, 5, 1, 2, 3, 9. So this is the inverse. So now I know, since this is the inverse, I can just flip it and I can get the actual graph that I want to graph. So we're gonna, this is x and this is log 2 x minus 1. So it's 2, 0, 3, 1, 5, 2, and 9, 3. So 2, 0, 3, 1, 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, up here somewhere, and then it's going to come along like so. And since that 1 is your asymptote, that's as close as it's going to get there. All right, now the domain, since your vertical asymptote is at 1, it'll start at 1 and go to infinity, and your range is unchanged. It's still all real numbers. All right, in our next example, we have log base 3x minus 1. So our domain is going to be the same as just your log base x. So our domain is still going to be 0 to infinity, and our range is still going to be all real numbers. The only difference here is we're going to take the log base 3x and we're just going to shift it down 1 unit to make it log base 3x minus 1, because remember that is your y-intercept. But I am going to do the inverse. So we got y equals log base 3x minus 1. So this is going to be x, oops, not yet. So this is going to be 3 to the y plus 1. I need to rewrite this. Y plus 1 equals log base 3 of x. I want to move that 1 over there with the y so that I can write this as 3 to the y plus 1 equals x. Now that I have that written in exponential form, I want to write it as an inverse. So this is going to be 3 to the x plus 1 equals y. So this is my inverse. So I'm going to create my table for the inverse. So 3 to the x plus 1. So let's choose, let's see, if we choose 0, let's do -1, 0, and 1. Let's just choose those. So we got 3 to the -1 plus 1, which would be 3 to the 0, which would be 1. 3 to the 0 plus 1 would be 3. And 3 to the 1 plus 1 would be 3 to the 2, which would be 9. So now if I graph that, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 1, 2, 3. All right, so if we graph the inverse, so -1, 1, 0, 1, 2, 3, and 1, 9. So here is the inverse. And then flip those numbers. So now you've got your x, and then this is your 3 to the y plus 1. So we got 1, -1, 3, 0, 9, 1. So now we go 1, -1, 3, 0, and 9, 1. And your graph is going to look like this. And again, it is a reflection over the line y equals x. All right, let's look at our next one. And we're going to do the same thing with this one to get our inverse. So we have, let me separate this with some squiggly lines so we don't get it mixed in. So we have y equals log base 4 x plus 2 plus 1. So this one is going to be a shift to the left and a shift up. So let's rewrite this. So this, I'm going to move the 1 over, so y minus 1 equals log 4 x plus 2. So now I've got 4 to the y minus 1 equals x plus 2. All right, I'm going to move that 2 over, so 4 to the y minus 1, not equals, just a simple minus will do. All right, so now switch the x and the y. So 4 to the x minus 1 minus 2 equals y. So this is our inverse. So now I can create my xy table here. And I'm going to choose points -2, let's see, -2, no, let's see. If I do a +2, a 3, I'm trying to look at my notes here. I think a 1 and a -5 maybe. They're all out of order because I was playing around with them when I was making this. So if I plug in a 2, so 2 minus 1 is 1, so 4 to the 1 is 4, and 4 minus 2 is 2. 3, so 3 minus 1 is 2, so that would be 4 squared, which is 16, and 16 minus 2 would be 14. 1 minus 1 would be 0, and 4 to the 0 is 1. 1 minus 2 is -1. And then, let's see, write this one out. 4 to the -5 minus 1 minus 2. That's 4 to the -6 minus 2. Why did I choose that one? So let's see. 4 raised to the negative 6 minus 2. So that gets me very, very close to negative 2, which if I take my x plus 2 and set it equal to 0, this is my vertical asymptote. So as negative 5, when I put it in the calculator, I get negative 0.199975, like everything's going to make the next number bump up. So as I'm approaching this negative 2, so I'm going to put about negative 2. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 1, 2, 3, 4. Okay, graphing takes so long. So let's graph the inverse. So 2, 2. And then remember, x equals negative 2 is your vertical asymptote. So I'm going to come over here and draw my vertical asymptote here. 3, 14. So 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's like up here somewhere. 1, negative 1. 1, negative 1. And a negative 5, negative 2. So this one is going to look like this. So that is the inverse. So now what does, and also, since your vertical asymptote is at negative 2, that means your domain is going to start at negative 2 and go to infinity. And your range is still going to be all real numbers. All right, so flip the script here. So now your x and your y's are going to change places. So you got 2, 2, 14, 3, negative 1, 1, and negative 2, negative 5. So 2, 2 is still a point. 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 3. It's like up here. Negative 1, 1. And then negative 2, negative 5. So it's like down here. So this one's going to come in like this. So you can see where the points are just mirror images of each other. But I find it easier to rewrite it in exponential form, switch the x and the y, and get the inverse. And then create my table for the inverse, then flip all my points to get my original equation. So translations and reflections of logarithmic functions are the same as for any other basic function. What causes a log function to be reflected over the x-axis? Question 1, what causes it? When the negative sign is in front. So when your negative sign is in front, that will cause, so this is my question 1. Question 2 says shifted horizontally. So shifted horizontally, what makes it shift horizontally? So this is when we have y equals log base a. So we're shifting horizontally. So this is going to be x minus some number. And shift vertically, this is going to be my question 3. So y equals log base a of x plus some number, plus or minus some number. So those same rules apply. Nothing changes. All right, properties. So this is where we're going to get into separating the information that's given to us a little bit. So if you are multiplying two things together, this is called your product property. You can break them apart and find the log of each number and then add those two responses together. So you would have log base a of x plus log base a of y. And this would be the sum of your two logarithms. All right, if you are dividing them, then you are going to subtract them. So we would have log base a of x minus log base a of y. And you would find the difference. They don't give you a lot of room to write these. The power property. So if you have a number raised to a power, you just put the power up front and then write the rest of it the same. So it's equal to the exponent multiplied by the logarithm of that number. And these make so much more sense when you actually start doing them with numbers. Log base a of 1. Remember, this means a to the 0 equals 1. So the log base a logarithm, if any log base a to 1 equals 0, it's always going to be the same, because anything to the 0 power will always equal 1. And then if you have a to the 1 equals a, this is always going to be 1. Okay, if you think back to writing them in their exponent form, it's always going to be the same. So let's look at this one here. We have log base 6 of 7 times 9. So I would find log base 6 of 7 plus log base 6 of 9. And that's how you would write it as a expanded expression. This one would be log base 9 of 15, not plus, minus log base 9 of 7. So here, this is log base 5 of 8 to the 1/2. So this would come out front. So you'd have 1/2 log base 5 of 8. Okay, remember, this would be log base a of m to the 2/3. This is your numerator, this is your denominator. So we would rewrite this as 2/3 log a m. Now here you've got multiplication and division and powers all in one. So what we're going to do is we're going to rewrite the numerator first. So that's all multiplication. So this is going to be log am plus log an plus log aq. Minus, and you're going to want to put parentheses because you have these two things happening here. So this is log base a p squared plus log base a t to the 4th. Because these two things are being multiplied, so you need to add those two together, but they're being subtracted from the stuff in the numerator. So rewrite it, because we got to now take care of the exponents. So the beginning is going to stay the same. So we're just going to rewrite that. Minus. So I'm going to distribute the minus sign to this. So this is 2 log base AP. And I'm going to distribute that negative here. Minus 4 log base AT. And this would be the expansion of E. So sometimes they don't give us near enough space. All right, this one over here. This one is really nasty. I'm not even going to lie. It's going to take a minute. I think I rewrote this one several times before I liked the way it looked. All right, so I'm going to enlarge this, and I'm going to rewrite this. So this is log base b, and all of this is to the 1. So this is going to be x cubed y to the 5th over z to the m to the 1 over n. I'm going to distribute the 1n to all of my pieces. So log base b, x to the 3 over n, y to the 5 over n, z to the m over n. So now I've got that. So now I'm going to take and turn this into my addition and subtraction. So we've got log base b, x to the 3 over n, plus log base b, y to the 5 over n, minus log base b, z to the m over n. I know these are so crazy. Now just put all the exponents out front and you're good. So 3 over n log bx plus 5 over n log base by minus m over n log base bz. And then we have expanded that one. All right. Now, this next one says, write each expression as a single log with coefficient 1. Assume all variables represent positive real numbers. A and B are not equal to 1. So these take a little bit longer. They wrote them expanded, and we're going to work them backwards. So what I know is these two are being added, so I'm going to multiply those two pieces. So this is going to be log base 3, and since I have this minus sign, I know there's going to be a division. But these two are going to be multiplied, so this is x plus 2x, and then 2 in my denominator. So that covers that one. All right, now this next one, I know since there's a 2 out front, this is m squared. So, and there's a minus sign here, so this is being divided. So I'm going to have log A. Actually, we can make that a little smaller. So we got log base A, and we know we're dividing. This is m squared and n cubed. And there's all that one. That one's pretty simple. This next one gets really crazy. So I'm going to write it first. I'm going to put the exponents back where they go. So we've got log base b m to the 1/2 plus log base b 2n to the 3/2 minus log base b to the m squared n. Now these two are being multiplied. So log base b, and then this is division, so we can go ahead and do our division because of this. So in the top we'll have m to the 1/2, 2n to the 3/2, and the bottom we'll have m squared n. So now I'm going to take and I'm going to distribute this 3/2 to the 2 and the n. I'm going to make this a little bit shorter here so I can use some space. So we got log base b. So we got m to the 1/2, 2 to the 3/2, n to the 3/2. Oops. I just distributed the exponent to both pieces. And then what I'm going to go ahead and do is, since I have m's and n's in the top and the bottom, and I know that I can move the smaller exponent either up or down, I'm going to go ahead and turn this because this is a 1 and this is a 2. So I'm going to turn those into fractions. I know that 2 is the same thing as 4 divided by 2. So I'm going to say this is m to the 4 halves. And 1 is equal to 2 over 2. So I'm going to say this is n to the 2 over 2. That makes it easier for me to add and subtract my exponents. So now 1/2 is smaller than 4/2, so I'm going to subtract 1/2. Now that goes away. Let me rewrite my log base b, get my fraction back here. So the m's are no longer in my numerator, but I have 4 over 2 minus 1 over 2, so that's m to the 3 halves. 2 to the 3 halves, I'm just going to say that's the square root of 2. So the square root of 2 cubed. And then I've got an n in the top and in the bottom, so I'm going to subtract 2 over 2, which makes that goes away, and subtract 2 over 2 here. So that gives me n to the 1/2, which we know n to the 1/2 is also a square root. So if actually I'm going to write n to the 1/2 up here, and I'm just going to write this as the square root of n because it's the same thing. So now I've got log base b, and this is this m cubed here. I'm going to borrow this space over here. This m, remember how I said if you can pull a 1/2 out, to pull a 1/2 out because you can get that square root. This would be m to the 1/2 cubed. So that would be the square root of m cubed. Or we could do m cubed to the 1/2. So now we're going to write, so in the top, this is, we got 2 square roots here. So that's 8n. And then in the bottom, we have a square root. So I can expand my square root symbol to reach the top and the bottom, and an m cubed in the bottom. And this is the final. So that's pulling in all of the rules into one problem, and it makes it super crazy. If it takes you a minute to go through this problem a couple of times, it's okay. It's a lot to grasp, and it's a lot to take in at one time. To answer this reflection question, says, can log base 3 x plus 2 be written as log base x plus log base 2? First of all, no, it cannot. The distributive property doesn't work that way. So we're going to say no, the distributive property doesn't apply here. All right. If you have to go back and rewatch this a couple of times, like I said, it's okay. It's a lot. All right, so here we're going to rewrite these. They're telling us that log base 10, 2 is approximately 0.301. So what we want to do is try to get these to have a log base or log 10 2 in them, so that we can do these without using a calculator. So my thought is, well, 4 is equal to 2 times 2. So what if I did log base 10 of 2 plus log base 10 of 2? Instead of writing it as a 4, what if I said 2 times 2? Then I know this is equal to that, so this is 0.3010 plus 0.3010. And that would be 0.6020. And because they gave me this piece of information, I'm able to type it in the calculator and go. Or not even type it in the calculator. You can just add the numbers together. Same thing over here. 5 is the same thing as 10 divided by 2. So what if I wrote this as log base 10 of 10 minus log base 10 of 2? Well, log base 10 of 10, remember that rule, it's just 1, minus, and log base 10 of 2 is 0.03010. So basically $1 minus 30 cents is almost 70 cents, so 0.6990. And our last rule on the theorem of inverses. So I'm going to give you the rule, and then I'm going to show you some examples so that you can tie it together with actual numbers. So you have log a to the log a of x. All of this cancels out, and it's just x. Log base a of x, that cancels out, and it's just x. So let me give you some numerical examples to make that make sense. If you have 7 to the log 7 of 10. Let's say that is what you have. All of that cancels, and your answer is just 10. If you have, it's my other example here, if you have log base 5 to the third, all of this cancels, and your answer is 3. If you have log base r to the k plus 1, it works with letters too. All of this cancels, and you're just equal to k plus 1. So just look at the examples to match up. You can apply these to any number. You have things that cancel out, and you're just left with the answer. The answer is literally in the problem, and that's what they're equal to. All right, have a great day.